Are you ready, Eilon?
Yes, I am.
Oh, then it's an honor, a pleasure to introduce the speaker, our speaker today, Eilon. Perhaps no need for any introduction, but some facts about him. So Eilon is a Nathan and Lily Silver Chair in Stochastic Models at the School of Mathematical Sciences in Tel Aviv University. And last but not least, he is the director of the Good to Know project, so which works with talents, I think. And of course, he's a major scholar in game theory and stochastic games, especially. And an extra thing about him that he's also a writer, a science fiction writer. Unfortunately, if I see correctly, his book's available only in Hebrew, so I don't know. Do you plan to translate this book into English, or it's enough if you translate it to Hungarian for me, actually. And today his talk is about repeated games with countably many players and TAIL-measurable payoffs. So it is not a fairy tale, it's a very scientific talk. And his co-authors are Galit Ashkenazi, Janos, Flesch, and Arkadi Predtetchinski. Galit is from Tel Aviv, Janos and Arkadi from Maastricht University. Eilon, the screen is yours. Please start your talk.
Yeah, thank you very much, Miklos. Thank you everyone for coming. So the talk indeed is on repeated games, many players, and general payoff function. So it all started last year in January, just before the COVID changed our lives. Janos was visiting Tel Aviv University. We've just, the four of us just finished another project, and Janos suggested working on repeated games with Borel payoff functions. That is general payoff functions, not discounted, undiscounted, this is for the kids, but real general payoff functions, nasty payoff functions, not continuous, not concave, nothing. So the only people I know that worked on repeated games with general payoff functions are Ashok Maitra and Bid Sadarth. So not too many people work on that. I understand why. I mean, I suspected that nothing can be done with such payoff functions with no structure. But heck, I mean, working with Galit and Janos and Arkadi is fun, and it promises many, many trips to Maastricht, which is a very nice city, so why not? So we started working on it, and actually in the last year, this last wonderful year, we had quite a few results on this topic, and the one that I'm going to present today is one of those results. And anyone who starts to work on repeated games with general payoff functions must start with the work of Blackwell in 1953, Blackwell and Stewart. So Blackwell and Stewart, back in 1953, they studied a very specific class of games, very special class of games, alternating move games. Zero sum. We have two players, player one and player two. Player one plays in even periods, 0, 2, 4, etc. And player two plays in odd periods, 1, 3, 5, etc. Note, time is discrete and it starts at 0. This is because those people were real mathematicians, set theorists, and set theorists start counting at 0 and not at 1. So in those games, the action sets are arbitrary, not necessarily finite, not compact, arbitrary action sets. So player one chooses an action, then player two chooses an action, then player one chooses an action, etc. And we have a winning set. The winning set is a subset of the set of infinite plays, and this is the winning set of player one. If the infinite play that the two players generated is in W, player one wins. If it is outside the W, player two wins. So this is the model that Blackwell and Stewart studied back in 1953, and they proved that if W, the winning set, is either open or closed, then the game is determined. That is, one of the players has a winning strategy. either player one has a strategy that guarantees that the infinite play will be within W, or player two has a strategy that guarantees that the generated infinite play will be outside W. So the game is determined. The question is, what happens when W is not open and not closed? And then Martin in 1975 proved that as soon as W is a Borel measurable set in the product topology, then the game is determined. Moreover, there is a pure optimal strategy, a pure winning strategy to that player who can win the game. So this is our starting point. And then one can ask what happens when the game is not alternating move, but what happens when the players play simultaneously. We can also ask what happens if the winning condition is not a winning condition, not a win-lose game, but there is some payoff function that depends on the infinite play. So this is the model that, again, David Blackwell studied in 1969. So in 1969, Blackwell studied this model. Player one and player two, they play simultaneously. In stage 0, they play simultaneously actions. In stage 1, they choose actions, stage 2, and so on. So this is a repeated game as the repeated game that we like, except that the payoff function is a general payoff function from infinite plays into the reals. Blackwell studied the model when the game is zero-sum, so that there is only one payoff function, player one maximizes, player two minimizes, and he assumes that the function f is actually a winning set. In Blackwell 1969 paper, f is a winning set. It is the union of countably many closed sets. And he proves that in that case, the game is not necessarily determined, but it has a value. Why isn't it determined? Well, because down here we have the matching pennies. The one-shot matching pennies falls into the class of those Blackwell games. The two-player may play the repeated game, but the payoff depends only on what they play in the first stage. And player one wins if they chose top left or bottom right. Player two wins otherwise. So we have a game with a winning condition, but there is no, the game is not determined. The value is 1/2. So in general, in Blackwell games, there is a value, but not necessarily the value need not be 0 or 1. So again, Blackwell proved that if the winning set is a countable union of closed sets, then the game is determined. Then in 1998, Martin made a huge leap, and he proved that in those games, as soon as the payoff function f is bounded and Borel measurable, then the game has a value in mixed strategies. I will talk about this proof in a moment. So this is our starting point at 1998. And then the natural question is, what happens in non-zero-sum games? Okay, so zero-sum games, again, this is for kids. What happens for non-zero-sum games? Do we have an epsilon-equilibrium? So as usual in games with non-continuous payoffs, we cannot expect to have zero equilibrium. Indeed, in this class of games, also, we do not have a zero equilibrium. For example, already in the single player case, if we have an action set of only 0, 1, then for a proper payoff function, we do not have a zero equilibrium. And what will be my discontinuous payoff function? So if the player chooses a bit in every period, then along the play, the player generates a number in the interval 0, 1, This is the binary representation. It chooses the binary representation of the number. And so the number that the player generates is the payoff unless the number is 1, 1, 1, 1, 1, 1, in which case we have a discontinuous payoff, the payoff is 0. So in that case, the value is 1 because the player can get a payoff as close to 1 as he wishes, but she cannot get the payoff of exactly 1. So we cannot look for 0 equilibria, we only can look for his epsilon equilibrium. But the question is still whether an epsilon equilibrium exists. By the way, also in Martin's proof in 1998, we assume that the number of actions is finite, as is written here. The number of actions is finite because in games, general games, discontinuous payoff games with countable many actions, we do not necessarily have an equilibrium. We will see an example later. So anyway, this is the question that we would like to solve, whether in every simultaneous move game with 2 players, finitely many actions, bounded and Borel measurable payoff, we have an epsilon equilibrium for every epsilon. This question is still open. So what will be our model? Our model will be, we will have a set I of players, not necessarily 2. We will have, and as the title of my talk suggests, we will have countably many players. AI is the set of actions of player I. It will be finite for every I. A is the product set of action profiles with the product topology. And a to the power n to the power integers. So a to the power n is the set of plays in the infinitely repeated game. And then for each player I, we have a bounded by 0, 1 and Borel measurable payoff function fi. So this is the model. Questions so far? Now, the question is still open, so we have to find simpler setups where we can do something. And then what we do is we study tail measurable payoffs. What is a tail measurable function? So a function f from infinite plays to 0, 1 is tail measurable if it doesn't depend on the first k stages, the play in the first k stages. That is, whenever we have 2 plays, 2 infinite plays that coincide from some point t and on, then we get the same payoff. Okay. So the payoff so the action that the players play in the first 5 stages or the first 10 stages or the first 20 stages do not affect the overall payoff in the game. So this is tail measurability. For example, there are many, many examples of such interesting functions. For example, if we have stage payoffs, so UT is the stage, the payoff at stage T is by a function UT from action profiles, and then the total payoff of a player is the lim sup, not the lim, but the lim sup of the average payoff up to stage T. So the lim sup of average payoffs is tail measurable because the lim sup of averages does not depend on the play in the first 1 million stages. Some other payoff function that is tail measurable. Suppose that we would like the action profile A star to play at all stages T that are prime numbers from some prime number and on, and it is 0 otherwise. So only if the action profile A star is played in stage 5 and 7 and 11 and 13 and so on, from some prime number and on, then I get the payoff of 1. So I do not know why I would like to have such a payoff function, but this is a tail measurable function. Computer scientists, they love tail measurable payoff functions. So if you the Bucci payoff function, this payoff function is one if the action profile is some pre-specified set of action profiles A star infinitely often. So if we chose either top left or bottom right infinitely often, then I get 1. Otherwise, I get 0. We also have a co-Bucci payoff function, which is 1 if top left and bottom right were chosen only finitely many times. So action profiles in the pre-specified set A star are chosen finitely many times. We have the parity evaluation, which means that we order the set of action profiles according to some order, and then the least action profile that occurred infinitely often is in some pre-specified set A star. We have a Muller payoff function, which is an action profiles appear infinitely often if and only if it is in some pre-specified action profile. And then I get 1, otherwise I get 0. Now, any function of tail measurable functions is tail measurable. So the sum of two tail measurable functions is tail measurable. The product, the whatever exponent, whichever function you would like to have is tail measurable. So there is a rich family of such payoff functions, and this is the class that we handle in this paper. Now, the discounted payoff is not measurable because the discounted payoff depends on the payoff in the first stages. The first 1 million stages determine the discounted payoff up to 1 minus epsilon. So, or up to epsilon, whatever. So anyway, the discounted payoff is not tail measurable. So we know now what is and what is not tail measurable. Now, if the payoff function is tail measurable, then the min-max value of a player is independent of the history, right? Because the history does not depend, the payoff in a tail measurable, when my payoff is tail measurable, my payoff is independent of whatever happened in the first 5 stages. So my min-max value is independent of what happened in the first 5 stages. This means that the history of the game does not affect, up to the finite history of the game, does not affect the min-max value. And this is an important property of tail measurable, of repeated games with tail measurable payoffs that we will use. So this is our main result. Suppose that the set of players is countable. Each player has a finite set of actions, and the payoff functions are bounded by 0 and 1, and they are Borel measurable and tail measurable. In that case, an epsilon equilibrium exists for every epsilon. Now, it is interesting to note that one-shot games with Borel measurable payoffs do not admit, and with Borel measurable payoffs do not admit an epsilon equilibrium. And this is an example we will see in a moment. It was given by Wurnevel, whom I've seen earlier here. So though one-shot games with countably many players do not admit an equilibrium, repeated games with countably many players and the tail measurable payoffs do admit an epsilon equilibrium. Now I would like to present a slight extension of the result. For that, let me introduce a new concept, a function f from infinite. Excuse me?
Maybe a preview of the example. Does the counter example that you mentioned for the one shot depend on the fact that there are countably many players?
Yes.
And generated for finitely many players?
No, because we know that for finitely many players, finite action sets, we know that an equilibrium exists.
Okay, yes, of course. Yeah.
So So this extension is dedicated to Abraham, and we will understand why, to Abraham Neyman. We will understand why in the next slide. So a payoff function f from infinite place to 0, 1 is called finite approximable if up to epsilon it is determined by a finite number of coordinates, like the discounted payoff. That is, for every epsilon, there is t and the function g epsilon from histories of length t to 0, 1, such that f of the infinite play is equal up to epsilon to g epsilon of the first t stages. So we can approximate the function f, which depends on the infinite play up to epsilon, by a function that depends only on the first t stages.
Eilon?
Yes.
When the action set is finite, as I see you do in this next theorem, isn't this just equivalent to it being continuous?
Yeah. Okay, yes. Indeed.
Okay.
Yeah, so a finite approximable is continuous. Okay, so this is a theorem by John Levy. And now, so if the set of players is finite, the set of actions are finite, the payoff functions are Borel, and the sum of a tail measurable payoff function and a continuous function, then an epsilon equilibrium exists for every epsilon. Okay. The proof is an immediate consequence of our existence proof, which is divide the game into 2. Okay, we fix epsilon. We would like to construct a 2 epsilon equilibrium. So let us approximate the, so we know that Fi, the payoff of player I, is the sum of a tail measurable payoff and a continuous payoff and a continuous function. So we approximate the continuous part up to epsilon by the first t stages, and then we essentially divide the game into 2 halves, the play up to period t and the play after period t. In the first t stages, we play an equilibrium in the game with the continuous payoff function. We ignore the tail measurable part because that is not affected by what happens in the first t stages. So we play an equilibrium for the continuous part of the payoff. And then after stage t, we apply our theorem to get an epsilon equilibrium in the infinite game after stage t. And this way we play in the first t stages a 0 equilibrium for the approximation of the continuous part of the payoff, and then afterwards an epsilon equilibrium for the tail measurable payoff. In this way, we get a 2 epsilon equilibrium in the original game. Note that here,
Eilon,
yes.
Can't you strengthen this result by a form that is saying that it is eventually tail measurable? That you say that for every epsilon.
I think that an eventually tail measurable is tail measurable. I think
you need an eventually epsilon tail, epsilon approximately.
It may be that for every sequence of 10 actions, 10 periods, there is a different tail measurable payoff function. So it is not a priori tail measurable, it depends on the first 10 coordinates and the tail.
Okay, so maybe it would work, I do not know.
Because then if it's finitely many players, you simply could take this finite horizon and put a terminal payoff, which is the payoff of this action plus the tail, plus an equilibrium of the tail game.
Yeah.
And you do backward induction.
Yes, that's true. This is, I think it is equivalent to what I said. I'm not sure, but you're absolutely right. Yeah.
And as long as Abraham is here, Abraham, don't you and Mertens have a result also on Borel payoff, equilibrium with Borel payoffs?
Yes, but this is in games with perfect information.
Ah, okay, all right.
Yeah.
Just vaguely.
So, yeah, so Mertens and Neyman indeed have a proof for alternating move games, multiplayers with bounded and Borel measurable payoffs, but not for simultaneous move. Okay, so then now why this slide extension, why did I mention it? This is because of the following result, a recent result due to Abraham Neyman, which considered the concept of valuations. So a function f, so suppose now that the players receive a stream of payoffs. In every period, the players receive a payoff, as we love in repeated games. So we have a stage payoff. And the only question is, what is the evaluation of a player for an infinite stream of payoffs? So suppose that my evaluation, so a function f from 0, 1 up to n, so stream of payoffs to R is evaluation if first it is Borel measurable. So we would like it to be measurable. Then we would like it to be additive. So the evaluation of the sum of two streams is the sum of the evaluations. And we also assume here a time value of money property, which is if we have two sequences, two streams of payoffs, x's and y's. So x1, x2 is one stream of payoffs, y1, y2, etc. is a second stream of payoffs. Suppose that the partial sums of x is always larger than the partial sums of y. Okay. In that case, if we value time, then we would like to get the money earlier. Then in that case, we would like to assume that f of the x's is at least as much as f of the y's. Okay. So we say that any function from infinite streams of payoffs to R is evaluation if it satisfies those three properties.
Eilon, since you quote me, so just terminology, the top definition is a definition of a measurable valuation. And you need still that f of the constant streams of 1 equals 1.
Yeah, so the
normalization.
Yeah, so indeed you have a normalization. I don't need it, okay, because you have something else in mind. Yeah, and this is indeed a measurable valuation. Eran, did you want to?
Yes, if it takes you too far, then ignore me. But can you give an example of a valuation which is tail measurable?
You mean this valuation?
Yeah, valuation according to this definition, which is tail measurable. Because I mean, my first guess would be that
you take a measurable Banach limit.
Is there such a thing as Borel Banach limit?
Yes. There is a Borel function that is in between the lim, which is a linear function on streams, which is in between the lim inf and the lim sup. You need the axioms of choice for it. Yes.
But it's Borel. It is Borel. Okay.
Borel or Lebesgue, that I don't remember.
Ah, Lebesgue. Okay, but you say Borel.
Yes.
Okay, never mind.
Okay.
I mean, my guess would be that any such Borel function, which is additive and also have any reasonable property, is immediately continuous. But maybe I'm wrong.
Okay. Oh, okay. So in that case, this theorem is really easy. In that case, but anyway, Merle and Neyman proved that every valuation is the sum of a tail measurable function and a finite approximable, a continuous function. And therefore, as a corollary of our previous result, in every repeated game with finitely many players, finite action sets, stage payoff functions, where the evaluations of all players of streams of payoffs are using such measurable valuations, then an epsilon equilibrium exists. Okay. So maybe there are indeed no such cases, and then it is a boring
in my paper, there is no, on valuations, nothing about measurability.
Right. You don't have measurability, but we need measurability. Yeah. Okay. So now let's go on to Vurneveld's example, counterexample for the existence of epsilon equilibrium in games with countably many players. Now, this example will actually lead us to the construction, to the proof of our result. So Vurneveld's example concerns a minority game. So we have countably many players. The players are 0, 1, 2, etc. Each player has two actions, 0 or 1, and the payoff of a player is 1 if he is in the minority. That is, we look how many players chose 1. But we have countably many players. So we take the upper density, the lean soup of the averages of players who chose 1. So if this lean soup, the upper density of players who chose 1 is strictly higher than half, then it means that the majority of players chose 1. And then I would like to choose 0. If the majority of players did not choose 1, then I would like myself to choose 1. So this is the example. And this is a variation of Peleg's example from 1969, when there is no 0 equilibrium. But in this example, there is no epsilon equilibrium for every epsilon smaller than half. And why is that? So suppose that there is an equilibrium X in mixed strategies. Consider the set E, which is the majority of players chose 1. So this set is tail measurable, but note here tail measurable is not with respect to time. This is with respect to players. We have infinitely many players, and therefore we ask whether the majority of players choose 1. So this condition is independent of the first 5 players. Whether the first 5 players chose 1 or 0 does not affect whether the set E, whether the choice of all players, the majority of all players is 1 or not. So this set E is tail measurable, and therefore by Levy's 0-1 law, it has probability either 0 or 1 under X. Okay. So it means that under the equilibrium, either with probability 1, the majority of the players choose 1, but then everyone wants to choose 0. In particular, those players who chose 1 would prefer to choose 0, or the other way around, with probability 1, the majority is 0, and then everyone wants to choose 1. And therefore, there is no epsilon equilibrium for epsilon smaller than half. Okay? I see that someone... Kolmogorov 0-1 law. Not Levy, are you sure? Anyway, I'm sure that you are more sure than me. So, Kolmogorov. Okay. So this is the one-shot example. And now let's consider the repeated game. So now the players are going to play Vurneveld's game in every period. What is the goal of the player in the infinite game? My goal is to lose Vurneveld's one-shot game only finitely many times. So I would like to win Vurneveld's game from some stage t and on. Okay, so this is the Fi payoff function, and it is tail measurable because I would like to win the one-shot game from some period t and on. And I claim that in this game, in this infinite repeated game with countably many players, an equilibrium does exist. And in this equilibrium, everyone gets one. So that everyone wins from some point on. And what is the equilibrium? Here it is. Okay. So in every period I, in every period t, players 0 up to t will play 1, and players t plus 1 up to infinity will play 0. So in stage 0, only player 1 will play 1, the rest plays 0. So player 1 is happy, he is in the minority, he gets 1. In the second stage, 1 and 2 play 1, and the rest play 0. So again, 1 and 2 are happy, they are in the minority, and so on. So in this case, in every period, almost all players play 0, but each player, I, from stage I and on, he is in the minority and he gets 1. So this is the 0 equilibrium that we have in Vournevel's repeated game. Now, how do we generalize this insight into a proof for any repeated game? So the idea would be to find an infinite play that yields all players a high payoff, where high means at least the min-max value minus epsilon, and then to play a green trigger strategy. So the players will follow this infinite play, and any deviation is detected immediately and punished. Okay, so this will be our approach. The only question is, how do we construct this infinite play? And this is the intricate point in the proof. So let us see how we do that. So for that, we go back to Martin's original proof. So again, in 75, Martin proved that alternating move games, zero-sum alternating move games with Borel measurable winning set W is determined. And in 1998, every 2-player zero-sum simultaneous move game with finitely many actions and bounded Borel measurable payoffs has a value. Now, to prove the 1998 result, Martin used the 1975 result. What I'm going to do now is to show Martin's proof. So this is Martin's 1998 proof. For every real number v, we define an auxiliary game, an auxiliary alternating move game, g of v, as follows. In this game, player 1 will define along the play a function d that is defined over finite histories. Player 2 will choose an infinite play in our game, in our simultaneous move game. So this is what they do along the play. Player 1 in the auxiliary game chooses a payoff function d, a function d from histories. Player 2 chooses an infinite play. So we set d of the empty history to be v. V is the parameter. Then at stage 0, player 1 will select a real number d of a0 for every action pair a0 that is possible in the first stage, so that player 1 actually chooses a payoff matrix. A payoff matrix over the action sets A1 and A2, which are finite. Now, player 1 is restricted to choose such Ds so that the value of the D that he chose is at least the D of the empty set, which was V. So this is a restriction of the choices of player 1. Then, in stage 1, the other player, player 2, selects one of those entries, an action profile A0 hat. Next, in the next stage, stage 2, player one will again select an A1 times A2 payoff function, D of the, so here it is A hat 0. It might depend on A hat 0. And this choice must satisfy that the value of this function is at least D of the A hat 0. Okay, so D of this quantity was selected by player one in stage 0, and the A0 hat was selected by player one in stage 1. And then again in stage 3, player 2 selects an action profile A hat 1, and so on and so forth. So in every even stage 2t, the players already chose D of all finite histories of length smaller than t, and player 1 and player 2 chose a history, a finite play up to stage t. And then in stage 2t, player 1 selects D of A0 hat, A1 hat, A2 hat, up to AT hat, and a matrix, such a matrix, such that its value is at least the D of the current history that player 2 chose, and then player 2 selects the continuation action profile. And the winning condition in this game is that player 1 wins the game if the lim sup of the D's of the partial histories is smaller than the F of the infinite history. So if the F of the infinite play is larger than the lim sup of the D, player 1 wins, otherwise player 1 loses. So this is the game that Martin defined, and the way we should think about this game is as follows. Suppose that player 1 would like to prove to player 2 that he can ensure that the value of the simultaneous move game is at least V. So this is the goal of player 1. The value of the infinite stage game is at least V. So how does he do it? He selects a value, some quantity D of A0 to every action profile A0. And then player 2, and the interpretation of this quantity D of A0 is that the value of the continuation game that starts at A0 is at least D of A0. So if indeed player 1 is correct, and the value of the continuation game is at least D of A0, then this condition that the value of D of A0 is at least D of the empty set means that if indeed the value of the continuation is at least D of A0, then the value of the original game is at least V, because the value of D of A0 is at least V. And then player 2 chooses one action profile, A0 hat, and says, okay, prove to me that the value of the continuation game is at least D of A0 hat. So to prove that, the players continue recursively. And if indeed at the end, the payoff to player 1 in the simultaneous move game is at least the lim sup of the D's, it means that he succeeded in showing that the value that is payoff is at least the D's. Okay. So this is Martin's construction. Now, how does so for every V, the game is determined. The higher V, the more difficult it is to prove that the value is at least V. So if V is small, then note that the only place in this game D of V that V is taken into account is D of the empty set. So the higher V, the less options player 1 has in the first period, and therefore he has fewer strategies and he can win less. So the lower V player 1 can, the more probabilities that for player 1 to win. The higher V, it is easier for player 2 to win. Therefore, there is V star such that player 1 wins for every V below V star, player 2 wins for every V above V star, and Martins proved that V star is exactly the value of the simultaneous move game. Now, what is important for us is the next statement, the following one, which is, suppose that V is smaller than V star. So player 1 can win Martin's game. Suppose we have a strategy pair in G of V under which we have a strategy pair in the original game, in the original simultaneous move game, under which D, the function D, is a sub-martingale. So such a strategy pair guarantees a payoff of V to player 1. So it guarantees a player V to the player. Okay. So again, if we have a strategy pair in the original game, in the original simultaneous move game, so under which D, this function D is a sub-martingale, so it increases in expectation, then this strategy profile generates a payoff which is at least V. Okay. Why is that? This is because if D is a sub-martingale after such a strategy, then the limit of the D's exists with probability 1. So this limit exists, and it is below F, because player 1 wins the game G of V. So what we know is that V is equal to the D of the empty set. Since D is a sub-martingale, the limit exists, and the expectation of the limit is at least D of the empty set. And this expectation is below the expectation of F, because player 1 wins the game G of V. Okay, so we know that such a strategy, which is under which D is a sub-martingale, guarantees high payoff. Now we can modify the function D so that it also satisfies a subgame perfectness condition, which is the value of the one-shot game D is at least V, not only for the history of length 1, but for every history. For after every finite history, the value of the D's is at least V. And now, given that, we can derive the following conclusion, which is after we change D in such a way, and if we have a strategy sigma under which this new D is a sub-martingale, then the expected payoff under such a strategy sigma is at least V for given any finite history H. Okay. So this change, this modification of D allows us to conclude this, this property, that is a function that under which D is a sub-martingale yields a payoff at least V to every finite history, given any finite history. And this is what we need. Sorry?
Eilon, this addition, is that due to the fact that it's tail measurable? This is where you use tail measurability?
No, here we still do not use tail measurability. Here we can do with Borel measurability. We need tail measurability in a moment to assume that, to show, because we assume that the value V is independent of the history. This is where we use tail measurability. So now we can prove our main result. So Martin indeed proved his result only for two-player zero-sum games. We can extend his result. It's not too difficult to extend it to any number of players, also to countably many players. Okay, with some caveat, I won't have time to dwell on it. We can dwell on it later after the talk in the question time. But anyway, Martin's result applies for games with countably many players. So we denote by VI the min max value of player I, and we denote by DI Martin's function D, but with respect to player I's min max value. That is, we initiate DI of the empty set by VI minus epsilon. So it is below VI, and therefore player I can show that he can win the game. He can prove that his min max value is at least DI of the empty set. And what we also know is that the value of the one shot for every history HT, the value of the one shot game of this matrix game, whose payoff is DI of HT and the next action profile is at least DI of the current history. And also we know that the value of this one shot game is at least VI minus epsilon. So this is what we take from Martin. Again, this is true whatever be the payoff function, Borel or TAIL. Now, in Vurneveld's game, repeated game, this was our zero equilibrium. What our equilibrium in our epsilon equilibrium in our repeated game will be similar. We are going to fix for every player I some action AI has, arbitrary action. This is the zero action that the players played before they become important in the Vurneveld's repeated game. So until stage I minus 1, I don't care about my payoff. I'm player I. I'm sure I will get my payoff after stage I. Until stage I will not get a payoff, and therefore I play the action AI has. What the other players will play. So the other players in every period I, we have only finitely many important players that we have to take care about. And we have to ensure that their D is a submartingale so that they get high payoff. How do we ensure it? Well, they will play an equilibrium in the one-shot game with continuation payoffs D. Okay, so in each stage T, in each stage T, player 0 up to T will play a one-shot game, will play an equilibrium in a one-shot game that involves only them, player 0 up to T. The other players, T plus 1, T plus 2, they play their dummy action. Okay, their action which is not important. So we fix them, we throw them away from the game, we are left with finitely many players. Now those players, 0 up to T, they play a game whose payoff is their continuation DI. Since they play an equilibrium in this game, the equilibrium payoff is at least the min max. So we have an equilibrium, which means that the expectation of the D of the continuation is at least the value of this game D, which is at least D of the current state. So the Ds are indeed the submartingale, and they are also at least VI. So that this submartingale gives us at least VI after every history, I mean, for every initial history. So this is the idea of the proof, that in every period, in every finite period, actually we have only a finite stage game because infinitely many players, T plus 1, T plus 2, they play a dummy action, and the rest, they play an equilibrium in a one-shot game with continuation payoff T. So this strategy profile, sigma star, under which this strategy profile DI is a submartingale from stage I and on, and therefore the expected payoff of player I after every history H is at least VI minus epsilon, at least the D of the empty history. And this is for every H. Now, if this condition occurs with probability 1 after every H, so it means that with probability 1, Fi must be at least Vi minus epsilon. So if the conditional expectation of F given every history is at least Vi minus epsilon, it means that Fi is at least Vi minus epsilon with probability 1. So we know that for every player I, Fi is at least Vi minus epsilon with probability 1, which means that there exists at least one infinite play under which all players get at least vi minus epsilon, and this is the play that we want for our equilibrium. We found one play that gives all players at least vi minus epsilon. And then we use a green trigger strategy. And that's the end of the proof. So if you ask where did we use tail measurability, so we use tail measurability first to assume vi is independent of the history. Okay, so here when we conditioned we said that the conditional payoff is at least vi minus epsilon. Okay, it is the vi of the current history, but it is the same for all histories. Also, which means that okay, and this is essentially where we use it. Now, this method of constructing a good strategy profile by playing an equilibrium in a one-shot game with continuation payoffs that are chosen in some way, our function b. This is actually adapted from an old paper of Nicolas Vieille and myself from 2002, something in stochastic games. So it was useful also here. So now I will end the talk with future research, open problems. So as I said, I don't know anything actually that was done on non-zero sum repeated games, simultaneous move with general payoff functions. Okay, so there is a lot of work to do. For example, the question I started with, two-player repeated game with finite action sets and Borel measurable payoffs, not tail measurable payoffs. Do we have an equilibrium or an epsilon equilibrium or not? So this is an open problem. We can also study stochastic games. Okay, so Nicolas Vieille proved in 2000 that every two-player stochastic game with finitely many states and actions, where the payoff is the lim sup of the average payoffs, the average stage payoffs, it has an epsilon equilibrium. What happens if we have tail measurable payoffs? Will we then have an epsilon equilibrium? So we have partial results on this question, but still nothing definite. Also, we can ask what happens in alternating move games, like the original games of Blackwell and Martin 75 with monitoring structure. So the players do not necessarily observe each other's actions. Eran Shmaya studied this problem when we have eventual perfect monitoring. So eventually the players know each other's actions. But what happens if you do not have eventual perfect monitoring? Then we have some extensions, but the question essentially is still wide open. Thank you very much.
The alternating move, you are speaking even on with monitoring structure, even for the two-person zero sum. Yes,
yes, two-person zero sum, even winning set, the winning set for player one, the basic model. And Eran, you can correct me if more is known about it.
I mean, I think there are easy examples that with arbitrary monitoring structure, there is no value, there is no equilibrium, but I don't know if...
Yeah, already in your paper, you provided example where in the general monitoring structure, there is no value, it not be a value, okay. But then whether in some specific, simpler monitoring structures, whether there is a value.
Eilon, so you have this epsilon equilibrium result. So my computer went on, so I joined to Helmut. So I'm sure that you have in mind some examples. Perhaps I can guess which ones. So have you looked at which is the limits of the epsilon equilibria? So you take the epsilon smaller and smaller, and then you have a sequence. And of course, because if you take the additive set functions, probability set functions of each star compact sets, it has some limits. Have you checked which are the limits in these concrete examples of your sequence of epsilon equilibria?
No, no. And whether you have a fault theorem, I do not know.
Okay, thank you.
Yeah, the question. Sorry.
No,
I was going to ask about the Fock theorem. It seemed to me that the TAIL measurability says that it's never too late to start punishing somebody, right? Mm-hmm. And it seems to me that you were saying that in the end, every path that is individually rational, every play path that is individually rational is supported by an equilibrium, and your argument was to show that there exists some path like that. Yeah, is it the correct way?
Yes.
So there is in a way some kind of a Fock theorem here that says that every payoff that is individually rational and is feasible in the game is supported by an equilibrium, or
yes.
and the difficulty is to show that there exists such a thing, or am I?
So indeed, every payoff vector that is individually rational and feasible by a play, by an infinite play, is an equilibrium payoff. But can we have additional payoffs that are not supported by a single play if we play mixed infinitely often? Okay. And we have examples that there might be such equilibria.
I am not sure to understand the issue of individual rationality for a Borel payoff function. So what do you mean a path that is individually rational?
It is at least
with respect to the initial individual rational level, or given any history of it?
So here we have TAIL measurability, and therefore we ignore.
Yes, but Eran was asking about the cases when there is no TAIL measurability. And there
no, I was talking about I meant the initial min-max level, and using the fact that with TAIL measurability they are the same throughout the game. I mean, I wasn't saying anything complicated.
TAIL measurability, okay.
So if you do not have TAIL measurability, then essentially you have a stochastic game, right? Because your actions in the past may lead you to a completely different payoff function. And therefore, essentially, you have a stochastic game with countably many states. Okay, and then even if when we have the payoff function is the limit of the averages, which is TAIL measurable, we do not know whether an equilibrium exists. Okay, so it's not clear how to handle such a case. Or actually, it is difficult. Okay, more questions?
If no further questions, then thank you very much, Eilon, again.
Thank you.